All right, in this example, we want to take a look at a system of equations where we only end up with two equations, yet we have three unknowns. Well, let's take a look at how we would attack that type of situation. So this problem states that a rug cleaning company sells three models. Easy model weighs 10 pounds packed in a 10 cubic foot box. The mini model weighs 20 pounds packed in an 8 cubic foot box. And the hefty model weighs 60 pounds packed in a 28 cubic foot box. The delivery van has 324 cubic feet of space and can hold a maximum of 480 pounds. So to be fully loaded, how many of each should the van carry if the driver wants the maximum number of hefty models? Okay, so if we just take a look for a moment, right, we're given information about the easy model. So the easy model weighs 10 pounds and is in a 10 cubic foot box. So let's just note, right, like the easy model is going to weigh 10 pounds. Let's talk about the weight here, and let's talk about the cubic foot size. So easy model, 10 pounds, 10 cubic feet. The mini model, let's use the letter M for mini. That weighs 20 pounds and is in an 8 cubic foot box. And then the hefty model, let's say H for hefty, is 60 pounds and that comes in a 28 cubic foot box. So the two constraints that we're given are that the delivery van has 324 cubic feet of space and it can hold a maximum of 480 pounds. So if we take the space constraint first, 324 cubic feet, so we have 10 cubic feet for each of the easy models. We have 8 cubic feet for each of the mini models, and then we have 28 cubic feet for each of the hefty models for no more than 480 pounds. Now, technically, that should probably be a less than or equal to symbol, but let's just make it equal to, and we know that as long as we don't go over that constraint, we're good to go. All right, and then the weight of 480 pounds total in the delivery truck. So the easy models, those are 10 pounds a piece for each easy model, and then we're going to have the 20 pounds for each mini model, and then we're going to have the 60 pounds for each hefty model. And we cannot go over the, you know what, I just did all of that backwards, didn't I? All right, so good, I just caught that mistake. The first equation that I just wrote was the space restriction. So that first equation was 10 and the 8 for the mini and the 28 cubic feet, and that cannot be more than 324 cubic feet. And then that second equation was the weight restriction. So now that we have the two equations set up here, right, notice the main issue in this case is typically if we have three unknowns, how many of the easies do we want to pack? How many of the minis do we want to pack? How many of the hefties do we want to pack? So we have the three unknowns there. We really need three equations in order to solve that system. And the issue with this particular scenario is we're only getting two equations. But we are told that we want to bring the maximum number of hefty models as possible. So basically, here's what we're going to do. I'm going to kind of take an approach of like we're going to plug and chug. So like if I could have, 10 hefty models, how many minis and easies could I get? Or if I could only have 5 hefty models, how many minis and easies could I get? So what I want to do is boil this down to two equations with two unknowns. And I, in essence, want to have the easies in terms of the heavy, and I want to have the minis in terms of the heavy, and that way I can plug in different values of the heavy. I can plug in 5 hefty models, 10 hefty models, so on and so forth, to see how I can optimize the scenario here. A couple different ways we can accomplish that, right? So let's say I take, let's call this equation 1 and equation 2. If I just subtract those equations, let's say I do equation 1 minus equation 2, so I'm going to have 10e minus 10e, and the e's go away. I'm going to have 8m minus 20m. That's going to give me negative 8. It's going to give me negative 12. And then if I do 28h minus 60h, that's going to give me negative 32h. And then if I do 324 minus 480, that's going to give me negative 156. Okay, so at this point I want to get the m in terms of the h variable, right? So I want to be able to plug in a value for the heavy and find out how many minis that would produce for me. So I'm going to take this equation that we now have here, let's call this equation 3, and let's solve for m. So I would have negative 12m equals negative 156 plus 32h. So I'm adding that 32h to the other side, and then I'm going to divide both sides by negative 12, and I'm going to get m equals, this is going to be 13, and then minus, 32 over 12h, which I could reduce that. So my m is going to be 13 minus 8/3 h. All right, now I want to get the e in terms of h as well. So actually I think what I'm going to do at this point, this technically now what we have here is equation 3. So to create equation 4 where I have the e in terms of h, I think I'm just going to take the m that we just created, our equation 3, I'm going to substitute that back into one of those prior equations. So I'm going to substitute equation 3 into let's do equation 1, I guess. Doesn't really matter which one I pick. So I'm going to be replacing m with 13 minus 8/3 h. So I'm going to have the 10e plus 8 times the m that we're substituting into equation 1 plus the 28h equals 324. So now I'm just going to do a little bit of arithmetic, some algebra here, and get e all by itself. So let's distribute the 8. 8 times 13 is going to be 104. And then when I distribute the 8 to this fraction, I'm going to have 64/3 h, and then plus the 28h. Equals 324. I'll subtract the 104 from both sides. So 324 minus 104, that's going to give me 220 over here. I have the 10e, and then I have the 28h minus 64/3 h. So getting a common denominator there, the h's, 28 minus 64/3, gives me 20/3 h equals 220, and then I'll subtract that to the other side. So I'm going to have 10e equals 220 minus 20/3 h, and then I'll divide everything by 10, or in other words, multiply by 1/10. So 220 divided by 10 is going to be 22, and then 20/3 divided by 10 is going to be 2/3 h. So let's call this equation 4. So in other words, my equation 3, I have the number of minis in terms of however many heavies I can fit, and then I have the number of easy models in terms of the number of heavies I can fit. So there's my equations 3 and equations 4. So again, the idea here is that I'm going to plug and chug. I'm going to take h equals 1, plug it in, see what I get. H equals 2, plug it in, see what I get, so on and so forth. So I want to maximize the number of heavy models. So remember, I'm going to come up here and circle that, right? So we're going to maximize the number of heavy models. So my question is, how many heavies can I get so that I still have the minis and the easies I'm able to bring with me? Now keep in mind, inherently in this problem, the numbers of minis and easies can't be negative. They have to be positive numbers, right? And they need to be integer values. So as we start to plug numbers into these equations, we're going to get some fractions or some decimals, if you will, right? And let's talk about how we're going to manage that. Okay, so to make my number crunching and substituting values for h as quick and efficient as possible, I'm using Desmos. So what I'm going to do in Desmos is click to add a table. And what I'm going to have my first column be is how many heavies am I going to bring. And then I'm going to let the next column be the minis. So we had what, 13 minus 8/3 times h for the minis. And then the easies, we had 22 minus 2/3 h. Oops, I want the h there. All right, so in other words, if I bring, one heavy, I'm going to be able to bring 10.3 minis and 21.3 easies. Now, obviously, you can't bring a fraction of a box, so we're just going to say 10 minis and 21 heavies. Now, if we bring 2 heavies, we would then be able to bring only really 7 full boxes of the minis and 20 boxes of the easies. If we do 3 heavies, then we could bring 5 of the minis and 20 of the easies. What happens if we get 4 heavies? All right, so if we bring 4 heavy boxes, we can fit in 2 of the minis and 19 of the easies. What if we do 5? Okay, if we do 5, now we're getting to an issue here. So we're not allowed to bring negative numbers of boxes in essence. So what we're going to say then is we're getting an invalid solution at this point. So we're going to go back up here and we're going to say the maximum number of heavies we could bring is 4. We're going to be able to bring 2 full boxes of the minis and 19 full boxes of the easies. So this example just illustrates the little bit more kind of challenging solution of when I have 3 unknowns that I'm solving within my system, but I'm only able to generate 2 equations based on the constraints given. We have to be told some preference in that situation, and in this case the preference was we want to maximize the number of heavy models. And then so we're in essence going to kind of plug and chug, so what I like to call it, right? So just in summary, what we wanted to do is take our 2 equations. We wanted to get the easy model and the mini model in terms of the hefty model so that we could plug in different values for the hefty and see how many minis and easies we could bring in an effort to bring the maximum number of hefty possible while keeping the other 2 values positive quantities.